This is section 2.1, Tables and Trends. Calculator settings for tables. Okay, again, we're going to be using our calculator to look at some values for the tables. It says we look at how to set up a table in the calculator for functions. To see the settings we used, that actually stands for table set feature of the calculator. The table set key is the far right key just below the screen of the calculator. It's the second key of the window key. So pressing the table set key brings up the following menus. So if you press table set, you get that menu. So to see it on your calculator, okay, there is table set. Notice this is the Windows key, which actually allows you to set window settings, but second table set, and you get this. Okay, so the table setup. The default is that it starts at 0, and this is read as delta table. It's the increment. It is by default 1, and these are by default auto as well. There really is no reason to change it to ask. So usually the value of the independent variable, the value of the dependent variable, and that's what those are standing for, we keep it at the default of auto. So the meaning of each of the settings is as follows. Number 1, table start, and that's what that stands for. Table start is the starting value of the independent variable. It will be the first value displayed in the table of values displayed by the calculator. It is called the initial value. It is possible to scroll to earlier or later values, but it's just that it's the very first one. It's the one at the top of the table when you first use it. So if you don't want to start there, you can always go back to a different value. It's no big deal. That thing, again, it's read as delta table. That's the Greek uppercase delta. Gives the value that should be added to or subtracted from the initial value as you go from one value to the other on the independent variable. Okay, it's also called the step size. It's going, or the increment. We're going in increments of whatever. It's the increments of the independent variable. The value of the dependent variable is determined by a function which is in one of the y's. Okay, so this is the increment or step size for the independent variable. Okay, the independent and dependent let you decide, do you want the calculator to ask you for the next independent variable value or dependent variable value, or you want to do it automatically. I would just do it automatically. Again, there's no reason to make the calculator ask you a bunch of stuff. It's just too much button pressing then. So for independent variable and dependent variable, we just leave it at auto. The only thing that we're going to be changing that really matters is the delta table. What is the step size? What is the increment size? The table start, again, you can scroll up and down. It really doesn't matter. So it's this one that matters. So once we have set up how the table of values is going to be looking, how it's going to look using the table set, we can then enter one of our enter functions into the y equals. And then the table key on the calculator is, let me get out of this, so second quit. The table is the second of graph. So it's kind of like instead of seeing the graph, I want to see the table of values. So the table again is the second of the graph key. So it's just another way the calculator displays functional values to us, either graphically or in the form of a table. So we're going to illustrate how to do this with a particular example. So we'll try to include all of the necessary details so you can follow along. So, illustration. We want a table of values for the function f of x equals 5 over 2 times e raised to the negative 0.34x power plus 1. We want to start at 0 and want a step size of 4. So that's our function, and these are our table settings. Okay, so here are the steps. Again, step 1. First, we enter the function of the calculator. We're going to put it in the y1 location. So 5 for the numerator, divided by the open parenthesis, 2, then the second of ln to get your e to the x, then the negative 0.34, then your xt theta n key, then get out of the exponent, plus 1, so that's the numerator, so close off your parenthesis, and you're going to have something that looks like that. I said numerator, it's actually the denominator. So let me go ahead and enter this into my calculator so we can play along with the home game. So my y equal, okay, 5 divided by, open parenthesis for the denominator, 2 second ln to get the e to the x, negative 0.34, get out of the exponent, plus 1. I'm done with my denominator, close parenthesis, and remember to get out of this, just quit. So I've got my function entered into y1. So we'll now quit the screen. Okay, well, second of mode is quit. Okay, then step 2. Set up the table using the table set. You're going to press second window to enter the table set. You get that following screen. Okay, remember, we wanted to start at x equals 0, and we wanted a step size of 4. So let me get my table set up here. So second table set. Remember, we start at 0, so it's fine. So you can either just press enter or scroll down using the arrow keys. It's your choice. Okay, my delta table, again, remember we had a step size of 4, so enter it. So to keep up with the slides here. So for table set, we can leave it at 0 or enter 0, your choice. Then press enter to move to the next value. Okay, delta table, we made it to be 4. So we get something that looks like that, which is where we are. Remember, it's flashing on the computer. On the calculator, it's actually flashing here. Remember, we're leaving that alone. So since we're going to let the calculator make the table of values, automatically we can either quit the screen, second mode, or you can just go straight to the table, your choice. So we're now going to display the table. Just press second of graph. Okay, now in this one I did the second quit. Here, again, I'm leaving those two alone, so I'm just going to do second table. And there's your table. It's starting at 0. Notice we're adding 4 every time to the x's. And then here are the function values. Notice after a certain stage, it fizzles out. It looks like it's staying at 5. Okay, it looks like it's staying at 5 all the time from 36 on. Notice even when x is 32, it's incredibly close. So there's our screen. Notice the highlighted one, which is the one at the very bottom, is the value of x that's displayed here. Remember, we started at 0, had a step size of 4. And with this table, it looks like I have a limiting value for the function of 5. So that's how you use your table setup. We can scroll up and down again using the arrow keys in order to see different values. We can see from the above table that f of 0 is 1.667, so on. So if I go backwards, see f of 0 is 1.667, like f of 8 is 4.4179, and so on. Notice it only displays so many digits here. Like if I wanted something to 6th place value, I'd have to actually go back and do the vars, y vars, function, and all that stuff. So we can use a table of values to see function values, to see trends, and to discover a limiting value. Now again, it looked like our limiting value was 5. Okay, we can also use it to plot points if we have to graph by hand. Like if for some reason you have to hand in pencil and paper type homework, or on a test in class. You can now plot your points. Okay, some examples. Okay, we now look at some examples by using a table of values created by the calculator. So number 1, set up a table of values for f of x equals negative x squared plus 4x minus 3, evaluated at x equals 3, 6, 9, and so on out to 33. Notice if the screen goes to 33, you're fine. We really can't make it stop somewhere. There was no stopping value for x. It just basically fills up what it can. So our solution. We're going to enter negative x squared plus 4x minus 3 into y1. So if you do that, you get this. So let me go ahead and enter it into our calculator. So let's quit that screen. Y equal, clear out the one that's there. So negative x squared plus 4x plus 3. Okay, we're done with the function, so I just quit. Okay, so we're going to enter the table set, make the appropriate settings. And we're going to start at 3, and it looks like the increment is also 3. I add 3 to get to this one, 3 to get to that one. So table start is 3, delta table is 3. So if we do it on our calculator, okay, so second table set, okay, we're going to start at 3. Our delta table is 3. And let's just go ahead and make the table now. Second table. There. And notice it does go out to 33. So here are our functional values. Okay, they turned out to be nice integers. There does not appear to be a limiting value. It seems to be getting larger and larger in the negative direction. So there's your table. course, in WebAssign, he might have boxes for you to fill in these values. If you had to have something in by paper, you would just actually have to transcribe that to a piece of paper. Number 2. Use a table of values to determine if f of x, which is this thing, has a limiting value, and if so, what is the limiting value? Okay, notice we're going to need parentheses around that guy, parentheses around that guy. Okay, to get a limiting value is you want to know what happens as x gets to be larger and larger and so on. So, our solution. Okay, first we're into the function into y1. Okay, so let me go ahead and do that. Okay, quit this screen. Go to y equal, clear that out one. So open parenthesis, okay, 3x squared minus 8x plus 1, close for the numerator, divided by, open for the denominator, 5x squared plus 13x minus 5, close, quit the screen. Okay, so I've caught up to my slide. Now, when determining if there's a limiting value, we usually want to know what happens for very large values of x. Now, when we say very large values, we mean large in the positive direction, large in the negative direction. So I'm going to have an initial value of x equals 0. So notice for the negatives, I can just scroll past 0 by going up. And a step size of 100. Now, if you want to be bold and daring, you can say, no, I want a step size of 1,000, or I want a step size of 10,000, or a step size of 500. Now, sometimes if you make your step size too huge, it's like all of a sudden you're there at the limiting value. You never got to see, did it ever have any other values? So you can sometimes be misled. So that's what it looks like. So go ahead and let me do that on our calculator. So second table set, initial value of 0. Now if you're stumped, I'm looking for a limiting value, what should I start at? Go ahead and start with 0. It's as good as any other value. Go delta table of 100. Just for fun, I'm going to change it. I'm going to change it to 1,000. Okay, no real reason, but I'm just going to go ahead and change it to 1,000 to see something happening. So then we just do second table. So notice at 0 you get negative 0.2, then you get this 0.59685, 59842, and so on. So let me look at this one. Okay, 59895, 59921, 599. Notice I'm getting closer and closer to what looks like 0.6. If I scroll down some more, it looks like I'm getting closer and closer to 0.6. Right, because see this 599, and those get bigger and bigger. So if I keep scrolling down, let's see if y1 looks like it's getting even closer to 0.6. Yeah, because now notice I've got more 9s and only the last digit is changing on our display. Okay, it seems to be settling out now at 0.5994. Let's go a little bit further. Oh, now it changed. Now, what could be changing are digits that are not displayed in our table. Okay, so now that 5 went up to a 6, in the last place that we can see. But notice what the value of x is. It's huge. So let's see if we can make it come up to be 0.6. Okay, again, keep your eye on that last digit. It's now a 7. Again, what's probably changing are digits that the calculator is not displaying for us. It's digits that are internal to the calculator, but we're not seeing anything. So it's staying at 7 for quite a while. It's still at 7. And notice I'm up to 125,000 now. Ooh. Okay, finally went to an 8. Okay, finally went to an 8. Let's see, can we make it go to a 9? And of course, after it went to a 9, it would then become 0.6. Okay, but again, look at my x value. My x value is incredibly big now. So I'm guessing a limiting value of 0.6. If we wanted to speed this up, let's go to second table set. Okay, let's leave it off where it was, but let's make the step size. Let's make it not 1,000, but let's make it 100,000. Oh, there it is, 0.666. It's not changing, right? 0.6, 0.6. Now notice, this has gone to scientific notation. Now what about for large negative values? So let me do my table set. Second table set. Instead of having the delta table be 1,000, I wonder if it'll take a negative number. Negative 100,000. Second table. I wonder if it'll take it. It did take it. Notice 0.6, 0.6, and now it's like 0.6001 and so forth. I'm willing to say that our limiting value is 0.6. Okay? So we saw that more playing with the calculator there. So with this one, with the value of 100 for our delta table, notice it doesn't get to 0.6 quite as fast. So we can scroll down, which is what we did, live and in person. That we get a limiting value looks like a 0.6. Okay. If you go to calculus, you'll discover that that value actually is 0.6. Okay. You need calculus techniques to actually prove that, but it is 0.6. Limiting value is 0.6. But it took a while to actually see it. Number 3, it says, it is known that the function f of x, which is equal to 8 over 4 times e raised to negative 0.09x plus 1, has a limiting value. Find the limiting value. If necessary, round to 3 places to the right of the decimal point. So notice in the previous one, it worked out to be 0.6, but you need to round. This one, because of the e, perhaps maybe we might have to round. Let's check it out. So we're going to enter the function into the calculator. And I'm going to start with x equals 0 and a step size of 10. Okay, if you're saying, no, I want to start with a step size something bigger, kind of your choice. So I may actually change it when we do it live. So looking at what we have here, 7.9903, 7.9961. Notice this 0.99 part is staying the same. I'm thinking it's going to be 8. But if we do it on our calculator here, so let's quit this one. Let's enter the function, so y equals, clear that out, 8 divided by, open parenthesis, 4, second ln, negative 0.09x, get out of the exponent, plus 1, close parenthesis. Let's quit that screen. Let's go to our table set. Okay, now, just using a step size of, table set. Using just a step size of 10, it looks like I'm getting 0.8 kind of fast. So let me start with 0. And let me increase, okay, let me clear that one out. Let me try my step size instead of 10. Let's try it to be, I don't know, 25. So let's just start looking at the table. Oh, 8, 8, 8, not changing at all. I wonder what's going on in the negative direction. Okay, notice in the negative direction, this e to the minus 9, those are getting incredibly close to 0. So the limiting value appears to be 8. Number 4 says, when the rent is $825 per month, all 300 apartments in an apartment complex are leased. It's kind of like all the apartments are the same. Now it says for each $25 increase in the monthly rent, 6 apartments go unrented. So it's kind of like they're pricing themselves to have a bunch of empty apartments. It says answer the following. Part A, find the revenue when the rent is $1,000 per month. Question B, write an expression that gives the number of rented apartments when there have been X $25 increases in the monthly rent. Question C, write an expression that gives the monthly rent when there have been X $25 increases in the monthly rent. Notice X is counting the number of $25 increases. That's what's going on in B and C. Question D, write the revenue function R of X when there have been X $25 increases in the monthly rent. Question E, what monthly rent will maximize the revenue? So we're looking at the top of a hill. Question F, how many apartments are rented when the revenue is maximized? So we're still looking at the top of the hill, just that there we're looking for the functional value. Okay, so our solutions. So remember, the setup is you start off with a rent of $825 and you have all 300 rented. And then you're increasing the rent in these $25 increments. And every time you have a $25 increase, you have 6 empty apartments. So question A, we need to find out how many times we had a $25 increase. Okay? So remember, the rent went up to $1,000 and it started at $825. So the increase amount is what you had, $1,000 minus what you began with, $825. So 1,000 minus $825, that's a total of $175. So to figure out how many $25 increases that is, take the $175 divided by 25. So the number of $25 increases is 175 divided by 25. You had 7. You had 7 $25 increases. Now remember, we know what the rent is. We're told it's $1,000. We just got to figure out how many apartments were rented. Because remember, the revenue is going to be the rent times the number of rented apartments. Remember, every time there was a $25 increase, and we know that there are 6 empty apartments. So the number of rented apartments is going to be the 300 you started with minus 7 times 6. Remember, there were 7 $25 increase, and every time there was a $25 increase, 6 empty apartments. You have 300 minus 42. There are 258 rented apartments. Okay, remember, 258 rented apartments, and each apartment is paying $1,000 per month. So the revenue is going to be 100 times 258, $258,000. Okay, now again, going back to what happened here, we had to figure out how many $25 increases there were. So the new rent minus what it started with, 1,000 minus 825, that gave you 175. To figure out the number of $25 increases, divide the 175 by 25. There were 7 $25 increase. So every time there was a $25 increase, you had 6 empty apartments. So the rented apartments is 300 minus the 7 times 6, which gave you 258. So your revenue is 1,000 times 258. See, now question B wanted us to find an expression for the number of rented apartments when there are X $25 increases, right? So the number of rented apartments decreases by 6 for each $25 increase. Now remember, there are going to be X $25 increases. So you're going to have 300, what you started with, minus 6 times X. Okay, what you started with, minus 6 empty apartments going unrented for every $25 increase. And there were X $25 increases, right? It says so right there. Okay, question C wants us to write an expression that gives the monthly rent when there have been X $25 increases. Remember, it starts off with $825 and then it goes up. So it's going to be $825 plus something. So the rent increases in $25 increments. Okay, we're going to have X of them. Okay, they're going to be X $25 increases. So it's going to be $825 plus 25X. Okay, the rent that you began with plus $25 times the number of $25 increases. Question D asks us to write the revenue function R of X when there have been X $25 increases. Notice B and C are also in $25 increases. If you think back to our section 1.4, the revenue is the price per unit times the number of units. So the price is the rent. So there's our rent, $825 plus 25X. That's the number of units. So the revenue is monthly rent times number of rented apartments. So remember, our monthly rent we found to be $825 plus 25X, and there's the number of rented apartments. So it's $825 plus 25X times 300 minus 6X. Okay. Now if you want to FOIL that out, that's entirely your choice. So here it is FOILed out. Whether or not it's worth the trouble to FOIL it out, I don't know. WebAssign would take that. I don't know if you gain any more information by doing this or not. You might, because notice if X is 0 in this expression, you get 247,500. Notice if X is 0, that means you didn't increase the rent. You left it at $825. Question E says, what monthly rent will maximize the revenue, right? So to find the maximum revenue, to find where it occurs, because that's really what we're looking for in that one. Excuse me, almost dropped something. To find where the maximum revenue occurs, we make a table of values for R of x and look for what value of x will give the largest value for R of x. So we start at x equals 0 because it doesn't make any sense to have any empty apartments. Use a step size of 1. That way we don't skip anybody. So we scroll down to see where the values of y1 reach a maximum. So if we do that, okay, so notice I chopped off the 0 because I wanted to see something getting bigger and bigger and bigger. So if I do this live, okay, so turn my calculator back on, get my y equal. Okay, clear out the one that's there. Okay, now I'm going to have to go back a slide to see what the function was. So let me go back a slide. Where is it? There. I'm going to leave it in the factored form. So open parenthesis, 825 plus 25x, close parenthesis, open the other one, 300 minus 6x, close. Okay, quit that. Okay, for my table set, remember I wanted to start at 0, and I want a step size of 1. So let's just make the table. Okay, what I'm looking for is the values of y1 to go up and then to start going down. So keep your eye on y1. Okay, notice it is going up, 257,400, 258,000. It's still going up, right? 258,300, 258,300, and now it starts going down. Starts going back down to 258,000. So notice it reached its maximum at either 8 or 9. So there are two values that are going to work. So let me go back here. So again, when x is 8 or x is 9, I've got a maximum value of $258,300. So looking at the table, there are two values of x that will do it. They have the same largest value, $258,300. Remember, these are dollars. They are at x equal 8 and x equal 9. So the revenue is maximized for either of these values. So the rent for x equal 8 is 825 plus 25 times 8, which is 1,025. Remember, these values of x, those are the number of $25 increases. And when for 9, it's going to be 825 plus 25 times 9. So either $1,025 per month or $1,050 per month. Those are the two monthly rents that will give you a maximum revenue. Because again, remember, 8 and 9 were the number of $25 increases. Remember, that's what x was measuring. How many $25 increases we had. And remember, the rent is the 825 plus 25 times the number of $25 increases. So either one of those two monthly rental charges will give you a maximum revenue. And we know what the maximum revenue is now. It's $258,300. So question F, from our table for Part E, we see that the maximum revenue is $258,300. Now you could have also been asked, and it wasn't asked, but it might be a good question, how many apartments were rented in order to maximize revenue? So if we were to do the number of apartments that were rented, for x equal 8, remember it would be 300 minus 6 times 8. Remember, every time there was a $25 increase, you had 6 empty apartments. And if the value of x was 9, you'd have 300 minus 6 times 9. So that's how you would figure out the number of rented apartments. You would actually go back to the answer that we had for Part B and fill in either x equals 8 or x equals 9. Now, it doesn't always happen that way, that there are two values that'll give you a maximum. But, you know, sometimes there are. It's no big deal. I've got one more. Number 5 says, exams are us. Purchases used college exams for $100 each. Kind of like if you guys sold the WebAssign test. If they purchase 2 exams, they have to pay $95. So notice, if they just buy one, it's $100. If they buy 2 of them, they'll get $95 each. So in general, for each additional exam after the first one, they get a $5 discount per exam. Question A, how much does it cost Exams or Us to purchase 6 exams? Question B, write an expression that gives the cost per exam if X exams are purchased. Question C, find the cost function C of X if X exams are purchased. And question D, what is the maximum price that Exams R Us can expect to pay? You know, like if they're buying these exams from you. Kind of like you're their supplier. And remember, $100 for the first one. You get a $5 discount per exam after the first one. Okay, our solutions. In Part A, if 6 exams are purchased, that's 5 more after the first one, right? Remember, the first one plus 5 more, that gives you a total of 6 exams. Remember, you get a $5 discount after the first one. So the discount per exam is going to be 5 times 5. Okay, one of these 5s is the $5 discount. The other 5 is the 5 more after the first one. So you're going to get a $25 discount on all 6 exams that you purchased. So the cost per exam is going to be $100 minus $25. Okay, remember, it starts off with 100, says so right there, and you're getting the $25 discount per exam. So you're going to pay $75 per exam, and you're buying 6 of them. So the total cost is 6 times 75. It's $450. Say, so Exams R Us will give you $450. Notice it seems like they should give you an extra $5 every time you brought in more than one. Okay, in question B, we're to write an expression that gives the cost per exam if X exams are purchased. And remember, you only get that $5 discount after the first one. So we're going to make a table to discover a pattern. Now, when we say make a table, I'm going to make it by hand. Okay, so the number of exams purchased and the cost per exam. Okay, now if one exam is purchased, remember, the first exam is $100. Okay, now if 2 exams are purchased, remember, you get that $5 discount per exam. So, $5 discount after the first one. So if 2 exams are purchased, the cost per exam is $95. Okay, if 3 exams are purchased, okay, remember, it's a $5 discount after the first one. So you've got 2 after the first one. So it's a $10 discount from the 100. So you're paying $90. Let's go to 4 exams. Okay, if you purchase 4 exams, remember the first one there you don't get the discount. But for the next 3, there's a $5 discount per exam. So 3 times 5 is 15. So you're getting that $15 discount. So 100 minus 15, it's $85. Remember, X exams is the number of exams that we purchased, right? If X exams are purchased. In this one, the $5 discount wasn't multiplied by 2, it was multiplied by 1 less than 2. Remember, these are the values of X. In this one, there was no discount. So again, if we think about this, 1 less than 1 is 0. So $5 got multiplied by 0. In this one, 1 less than 2 is 1, and that was multiplied by 5. Here, X is 3. 1 less than 3 is 2, and that's what did the discount. Here, X is 4. 1 less than 4 is 3, and that was multiplied by the discount. So, it looks like we subtract $5 after the first exam. So instead of subtracting 5x for X exams, we subtract 5 times X minus 1. 1 less. Remember, and this 1 is, remember, the first exam. You don't get a discount for the first exam. So you're going to subtract 5x minus 1 from the original $100 per exam. So the price per exam is going to be 100 minus 5x minus 5 times x minus 1. If you want to multiply that out and have 100 minus 5x plus 5 and have 105 minus 5x, that's your choice. Okay, so either one of these is acceptable. So anyway, that's the cost per exam. Okay, question C wants us to write the cost function. Okay, the cost is going to be the number of exams times the cost per exam. All right? Now, this was the cost per exam. Again, either one of these values you like. Remember, how many exams are we going to sell? X of them. How many exams are we going to purchase? X of them. So it's going to be X times 105 minus 5x, or if you distribute the X, 105x minus 5x squared. Again, either one. Or if you wanted to put this whole thing in parentheses and have X times 100 minus 5 times X minus 1, that's fine too. Anyway, there's your cost function to Exams R Us. Okay, question D says to make a table of values to find the maximum value of C of x. Okay, we're going to start with 0 and use a step size of 1. Okay, so here are my results. So I want to notice that y1 is increasing, and then I want to see where does it start to decrease. So 340 to 400 going up, going up, going up, going up, going up, 550, 550, and then it starts going down. Notice it goes down in the same way it went up. Once again, it looks like two values. There are two values of x that will work, and the maximum cost is going to be 550. Now, we want to find the maximum value of c of x. That means we want the y1. The maximum value of c of x is $550. So the maximum amount that Exams R Us can expect to pay is $550. So notice that means if you're selling exams to them, that's the most that you're going to make is $550. That's the end of section 2.1.